Hello and welcome. In this problem, we have been asked to determine the value of specific heat, Cv, at constant volume for a gas. The data supplied are how U changes with temperature. If you quickly do a simple sketch of how U changes with temperature, you will see that the data given is exactly linear. In other words, U changes linearly with temperature, making the problem very simple to solve. So what is the definition of Cv? It is, as you know, is the partial of how U changes with temperature at constant volume. If you want to estimate this partial, it becomes simply a simple difference in EU divided by temperature. And we want to find the Cv at 350 Kelvin, which means to find the derivative at that location, all you have to do is to find how much is the change in temperature and change in EU and divide the two. As you can see, 350 being the midpoint is a perfect differentiation, central differencing, producing 1 over mass is 5 in this problem, and the change in EU is 1500 to 2000, so it is 2000 minus 1500, and change in temperature is 400 minus 300. So the answer boils down to a simple 500 by 100, which is simply 1 kilojoule per kg K. Now let's take this problem one step further. Suppose we have carbon dioxide in a rigid tank. We'll make up a problem and how we can calculate Cv for in more practical circumstances where you don't have the simplified data given. So for that, what we do, we launch a test step. In this case, we want to find properties, so we'll open system states. And let's say we are talking about an ideal gas, a carbon dioxide. So we open the ideal gas app, and let's make up a quick problem. So we have carbon dioxide, CO2, which is CO2, and let's say we have a tank of volume 1 meter cube containing carbon dioxide mass. Let's say we have just 10 kg of carbon dioxide. We are just making up a problem, and we want to find the Cv value at 350. So we'll take a temperature maybe slightly below 350, let's say 345, and find the state by clicking the calculate button, and we find a neighboring states. Now the temperature this time will peak 355. Volume will remain constant, and of course mass will not change. It's a rigid tank. So we have found two neighboring states, 345 Kelvin and 355 Kelvin, which is 350 being at the center. So what is the Cv value in that case? The Cv value will be in the IO panel. We can quickly calculate Cv. So we have delta U equal in kilojoules equal U2 minus U1, or actually, okay, mass times U2 minus U1, because we have specific internal energy, and delta T in Kelvin, T2 minus T1. Okay, so let's make sure so far so good. So we calculated U, delta U, and delta T, and their ratio is our Cv, which unit will be kilojoule per kg K, would be equals delta U in kilojoule divided by delta T in Kelvin. Capital K. Let me change that to capital K. Calculate. So we have found, oh, there is an error in my expression somewhere. Delta U in kilojoule. Okay, let me cut and paste. It's always a good idea. Now we are done. So we found the CV value to be 7.06 in this case for a particular gas, carbon dioxide. So what I'm trying to say is that once you know the behavior of how the internal energy changes with temperature, you can find the derivative for any gas or any substance for that matter. All you have to do is to pick your substance, in this case carbon dioxide. In this case we are treating a gas, but you can find CV or for that matter CP, any thermodynamic properties which depends on the derivative in this manner. Find two neighboring states and then you can calculate the derivative of any property in the IO panel in this manner.